Hello everyone, welcome back to this Unity tutorial series on how to create a roguelike like Vampire Survivors. We've made significant progress since embarking on this journey, and if you've been following along since the start, you should now have the framework in place for your very own roguelike shoot 'em up just like Vampire Survivors. Yet, as we know, a game is not just its mechanics. The aesthetics, play experience, and smooth performance are the elements that truly shape the overall enjoyment of the gaming experience. Now, equally important is the process of identifying and eliminating those pesky bugs that may have slipped through during development. Therefore, in this part, we'll actually take a break from introducing new features and shift our focus towards refining and polishing what we've already built. We'll devote our attention to ironing out any potential bugs that may have sneaked into the game along the way. While this may appear as a minor diversion, these finishing touches are what can elevate our game from being good to outstanding. Our ultimate goal in this part is to prepare the game for being played outside of the Unity editor, which means we'll be building the game so that you will have the opportunity to share your creation with others. And by the end of this part, you should have something like this, which is improvements to the enemy spawner, improvements to the map generation, other code improvements. We'll also be changing all text to TextMeshPro, and we'll also be adding a visual cue to the items. We'll also be making a title screen, and last but not least, of course, we will be building the game. And without further ado, let's begin. Let's kick off by addressing and resolving issues in the enemy spawner to enhance the player's experience. So the first item on our agenda is to tackle the problem of wave skipping. So some of you have already highlighted this issue in the comments of the previous parts, but for those who are unaware, let's conduct a quick test to understand the problem with the waves and why the changes are necessary. If you followed closely with the tutorial series thus far, your enemy spawner should have similar fields to mine, containing only 2 waves. However, if you have set more than 2 waves, go ahead and temporarily remove any of the additional ones for this test. Do remember to note down the details of those waves so you can re-add them later. Now, let's start playing from the menu scene. Once in game, select the enemy spawner object and direct your attention to the inspector panel. You should observe that the current wave count begins at 0 after the designated wave interval elapses, and it should change to 1 afterwards. At first glance, everything appears normal. The current wave count is supposed to increment after the wave interval, allowing the second wave to commence. However, if you navigate back to the game scene and add in an extra wave to make it 3 in total, then start playing, you'll notice an unexpected behavior. Instead of incrementing to 1 after the wave interval, it somehow just jumps straight to 2, causing the second and third wave to begin simultaneously. This bug disrupts the intended progression of the waves and affects the game's balance. Our goal is to rectify this semi-game breaking issue and ensure that the waves are triggered accurately, which is one after another. So to make this issue more noticeable, you can feel free to experiment by adding more waves and observing the behavior. Regardless of the amount of waves that you create, after the first wave interval elapses, the current wave count will be incremented to the index of the last wave. So why is this happening? Well, surprisingly, the root cause of this problem is much simpler than you might expect. If you navigate to the enemy spawner script and look under the update function, you'll notice that it checks 2 conditions, which executes 1 per frame. When the condition is met, it calls the begin next wave coroutine. However, there is a fundamental flaw in this approach that leads to the issue that we've been facing. The potential problem lies in the fact that if the condition remains true for more than 1 frame, the begin next wave coroutine will be initiated repeatedly, resulting in multiple instances of the coroutine running concurrently. To address this problem, we can simply introduce a boolean variable to track whether the coroutine is already running. Here's how we can implement the solution. To begin, let's create a boolean variable called isWaveActive and initialize it as false. Next, before starting the coroutine, let's add in an additional condition to check if isWaveActive is false. Then, at the very beginning of the begin next wave coroutine, set isWaveActive to true. What this does is that it ensures that the multiple waves won't start simultaneously because there is that additional condition. Finally, after checking if a new wave exists, set isWaveActive back to false. This allows new waves to begin as intended. Now, let's head back into the editor and test our changes. You should observe that the current wave count is now incremented correctly after the wave interval elapses. This ensures that multiple waves won't start simultaneously, effectively resolving the issue of wave skipping. After this, feel free to re-add/delete away any of the waves that you use for testing as they are no longer needed. Next, let's address another issue with the enemy spawner script, which is what I like to call the maximum enemies delay. So, what exactly does this mean? If you recall, we implemented a system in the enemy spawner script that disables the spawning of new enemies once the enemy count reaches its maximum, regardless of the current wave. And once the number of enemies drops below the maximum, spawning resumes. While this system functions correctly overall, upon closer inspection, you'll notice a small issue. Let's stop playing the game and examine why a fix is necessary. During gameplay, wait until the maximum number of enemies has spawned. Pay close attention and you'll notice a slight delay before the max enemies reach bow is checked. Similarly, after killing an enemy and bringing the enemy count below the maximum, there is a slight delay before the max enemies reach bow is unchecked. These delays are not ideal as they introduce unnecessary lag in the gameplay experience. Thus, to resolve this, let's delve into the enemy spawner script and identify the root cause of the issue. If you closely examine the spawn enemies method, you'll notice that we are setting the max enemies reach flag to true only before instantiating the enemy prefab. This actually leads to a delay in enabling the max enemies allowed flag because it needs to go through an additional iteration of the loop before the flag is set to true. Instead of doing this, what we can do is we can optimize this by moving the if statement that checks if the enemies alive is equal or greater than the max enemies allowed immediately after spawning an enemy prefab. This change ensures that the max enemies reach bow is checked promptly. By checking this condition right after spawning an enemy and incrementing the enemy's alive count, the script can halt the enemy spawning process as soon as the maximum allowed enemies are reached. Now it's time to address the delay in disabling max enemies alive. Similar to enabling max enemies alive, we can resolve this by just moving the relevant code block. Currently, we check if the enemies alive count is less than the max enemies allowed at the end of the spawn enemies method, which is really not ideal. This is mainly due to the frequency at which the spawn enemies method is called. If you look closely, it only calls when the spawn timer reaches the wave's current wave count.spawn interval. Consequently, what this does is that the check for the max enemies reach would only occur during these specific intervals. However, enemies can be killed at any point during the gameplay and not just when the new ones are being spawned. To address this, we can move the code that disables max enemies reach flag directly into the onEnemyKilled method. If you recall, this method is actually called when an enemy is killed. By making this adjustment, we can just ensure that the enemy spawning can resume as soon as the number of enemies alive falls below the limit, regardless of whether new enemies are being spawned. This modification will contribute to a smoother gameplay experience. Now, let's test our changes. Return to the editor and begin playing the game. This time, when you wait for the maximum number of enemies to spawn, you'll notice that there is no delay for checking the max enemies reach flag once the enemies alive count reaches the max enemies allowed count. Likewise, you'll observe the same smooth behavior after killing an enemy and bringing the enemy count down from the maximum limit. With these adjustments, the updated script should function more effectively. Great! Now, let's move on to something that a lot of you have requested me to revisit, which is the map generation. Many of you have pointed out several issues with the map generation, so let's just tackle them all now and tidy things up. The first problem becomes apparent during testing. So if the player is being pushed by enemies, the chunks do not spawn. To observe this, let's increase the max health of one of our characters in its scriptable object to an extremely high value and just allow the enemies to push the player. You'll notice that the chunks fail to spawn despite the player being pushed in a specific direction. So why does this happen? Well, if you recall, the map controller script has a relatively simple design. It uses the player movement script to determine the player's movement direction through the moveDir variable. The map controller would then utilize this direction to decide where to spawn the next chunk of the terrain. If there's no terrain in the direction, a new chunk would be spawned. And there is the problem. So, our game mechanics include enemies that can push the player around. And this created an issue for the map system. If an enemy pushes the player into an area with no terrain, the map system wouldn't spawn a new terrain there because it was still relying on the player movement direction, rather than the actual movement caused by the enemy's push. Consequently, what this does is that the player could be pushed into a void without any terrain, significantly disrupting the gameplay experience because you can see the background. To resolve this, we need to make substantial changes to the map controller script. Let's open up the map controller script and address these issues. First, we need to remove the dependency on the player movement script by not fetching it in the start function. Yeah, we can just eliminate the PM variable altogether. This means that the script will no longer rely on the player's input to determine the character's movement direction. Similarly, we also need to remove the section of the code that checks for each possible movement direction of the player. Since the PM reference has been removed, if we leave this code in place, it will just cause a lot of errors, so it's just best to just remove it temporarily. Now, let me explain the approach that we're going to take. Essentially, we'll just compare the player's position in the current frame to their last recorded position. This will allow us to precisely calculate how the player has moved during that frame. We will represent this movement with a vector, and we'll just call it moveDir for consistency, which includes both a direction and a magnitude. So this approach won't rely on any external scripts or components like player movement, and instead it will provide us with the true movement of the player regardless of the cause. So be it external forces or the player's input or the movement direction basically. This system will offer a more robust and reliable way to determine the player's movement direction. Now let's get started with the necessary steps. First, we'll add a new variable called player last position. This variable will keep track of the player's position in the previous frame. In the start method, we will initialize this variable to the player's starting position because we need to know the position from which the player begins at. Next, we'll do a little bit of math and we'll calculate the player's movement direction by subtracting the player's last recorded position from their current position within the chunk checker method. Additionally, after calculating the movement direction, we must update the player's last position to ensure that it reflects their current position accurately. If you recall, in the initial script, we determined the movement direction in a somewhat cumbersome manner, using a very large code block consisting of if statements within the chunk checker method. Thus, to improve our code and reliability and efficiency this time, we'll take a different approach. We'll create a new method called getDirectionName that returns a string. This method will effectively take in a vector3 argument called direction and will determine the name representing the direction. First, we'll normalize the direction vector within the method. Normalizing a vector adjusts its length to be 1 while preserving its direction. This normalization just ensures that we are working with consistent units and simplifies the comparison of the vector's x and y components. Next, we'll have to determine whether the movement is primarily horizontal or vertical. To achieve this, we'll use the mathf.abs function, which returns the absolute vector of a number. By applying this function to the x and y components of the normalized vector, we obtain the magnitudes of movement in each direction regardless of their sign, which is regardless of being positive or negative. We can then compare these magnitudes to ascertain the primary direction of movement. Now let's move on to determining the secondary direction of movement. And within each primary direction of movement, which is horizontal or vertical, we have three possible cases to consider. The movement is purely in the primary direction, meaning there is no secondary direction, meaning it's only vertical or horizontal. The second is the movement is partially in the positive secondary direction, which is diagonally up or right. And the third one is that the movement is partially in the negative secondary direction, which is diagonally down or left. To handle these cases, we'll use if statements. Let's start by focusing on the horizontal movement. Proceed to do the same for the vertical primary movement. Finally, for each possible combination of the primary and secondary movement, we need to return the appropriate string representing that direction. This involves comparing the x and y components of the direction vector again. But this time, we need to determine the sign, which is positive or negative, of the movement in each direction. To accomplish this, let's use a ternary operator to streamline the code and reduce the number of lines. You may have encountered the ternary operator before, as it's represented by a question mark. In essence, the ternary operator is a concise way to make an inline conditional choice between two values. So the basic structure of the ternary operator is as follows. So in this construct, the condition is the Boolean expression. And if the condition is true, the ternary operator returns value if true. Otherwise, it returns value if false. You can just think of it as a compact if-else statement. Let's apply this into the code starting with the horizontal primary movement. Let's also do the same for the vertical primary movement. With that step completed, we can now move on to spawning the chunks based on the string returned by the getDirectionName method. However, before we do so, we need to make some modifications to the spawnChunk method. In our initial code, the spawnChunk method was designed to spawn a new chunk without terrain in a specific position determined by the noTerrain position variable, which was previously calculated based on the player's movement direction. However, since we removed the reliance on player movement, we also need to make a change. Let's remove the noTerrain position variable and instead use a vector3 argument in the spawnChunk method called spawnPosition to represent the position where the new chunk should spawn. By directly passing in the spawn position as an argument to the spawnChunk method, we eliminate the need for storing the position with noTerrain in a separate variable. In the chunk checker method, after calculating the player's direction, let's create a local string variable called directionName. We'll assign it the value returned by getDirectionName method, passing in movedir as the argument for the appropriate direction. Once we have the direction name, we can just proceed to check if there isn't already a chunk at the corresponding position, just as we did in our initial code. To accomplish this, if you forgot, we'll use a physics2d.overlap circle. The checker radius and terrain mass parameters define the area and target of this check. So if the overlap circle returns false, indicating that there is no chunk at that position, we can then call the spawnChunk method. We'll pass in the same position we checked, which is direction name, as an argument. This will then ensure that a new chunk is spawned at the designated location. So let's summarize the general flow with an example. So let's consider a scenario where the player is moving in the right up direction. So in the next frame, when the player is moving, the update function is called, which triggers the method of chunk checker. And within the chunk checker method, the movement direction is calculated by subtracting the player's last position from the player's current position. Afterwards, the name of the direction is then obtained by invoking getDirectionName with the right up vector. And last but not least, the chunk checker then verifies if there is a terrain present in the right up direction from the current chunk. And if there isn't, it calls spawn chunk to generate a new chunk in the right up direction. With that said, let's return to the editor and conduct a test. You should observe that the chunks are now spawning in the direction the player is being pushed in by the enemies. Great! Once you're finished testing, remember to also restore your character's max health to its original value. The second issue we'll address with the map generation is the inconsistent spawning of chunks when the player moves diagonally. So many of you have noticed that when the player moves diagonally, the adjacent chunks of the diagonal chunk fail to spawn, resulting in a disruption of the map generation effect. So to demonstrate this issue, you can just begin playing and move in a diagonal direction. You'll notice that most of the time, when the player moves diagonally, only the diagonal chunk is spawned, while the neighboring adjacent chunks remain unspawned until the player changes direction. What this does is that it creates an inconsistency in chunk spawning, which can significantly affect the overall map generation experience. So we need to resolve this. To address this issue, we need to enhance our map generation by considering the diagonal player movement. So when the player moves diagonally, we need to anticipate that they may eventually move towards one of the adjacent directions. Therefore, in addition to spawning a terrain chunk in the primary diagonal direction, we also need to spawn chunks in the two adjacent directions. So let's imagine an example. Let's say if the player moves in the right up direction, then we want the map controller to not only spawn a chunk in the right up direction, but also in the up and the right directions. This ensures that if the player changes direction to either being straight up or straight right, they will still encounter a terrain chunk. To implement this solution, let's reopen the map controller script and locate the chunk checker method. Currently, this method only checks for a terrain chunk in the direction of the player's movement. We need to modify it to include checks for the terrain chunks in the adjacent directions when the player is moving diagonally. Within the if statement that determines the direction of the chunk to spawn, after spawning that chunk, we will need to perform additional checks for the adjacent chunks in the case of a diagonal chunk. Let's start with an example of checking if the player has moved in the right up direction. So in this case, we need to check if the chunks are already present in both the up and the right directions as they are adjacent to the right up chunk. And if there are no chunks in those positions, we simply need to spawn them. Now, you might be wondering why I'm using contains to check if the direction name contains both up and right instead of just directly checking for right up. Well, the contains method is used to check if a given string exists anywhere within the checked string. Thus, if we use contains right up, it would actually return true for not only the direction string right up, but also for strings like up right, right upper, or any other string that includes right up as a substring. This behavior is actually not desired in our context in case any of you have a different string from mine. In our case, the direction name can have 8 possible values: up, down, left, right, right up, right down, left up, and left down. By using separate contains up and contains right checks, we can actually ensure that we accurately detect right up, regardless of the order in which right and up appear in the string. It's also important to note that we are not solely interested in whether the direction string is exactly right up. We want to also know that if the player is moving both upwards and to the right, which applies to both right up and up right directions. Thus, by using a separate contains up and contains right checks, we can accurately identify both cases. Therefore, it's just better to use a separate contains check for up and right rather than a single contains right up check. Now, let's move on to handling other directional directions, which is left up, right down, and left down. We can use similar logic by checking if direction name contains both up and left, right and down, or left and down. This will ensure that the adjacent chunks are spawned correctly for these diagonal movements as well. Now, let's head back into the editor and conduct a test. During gameplay, move diagonally once again. This time, you should observe that both neighboring chunks of the adjacent chunk spawn alongside it. Awesome! Before we proceed on from the map generation, let's also take a moment to refactor the chunk checker method for improved readability. Similar to how we introduced the getDirectionName method to replace the redundant direction checks in the initial code, let's apply the same principle to the checking of the adjacent chunks. This will not change the functionality of the code, so do not worry, but it will potentially improve efficiency. So currently, the chunk checker method contains repetitive logic that checks if a chunk exists in a given direction, then spawns a new chunk if it doesn't exist. This repetition makes the method lengthy and somewhat challenging to comprehend. So to address this, let's abstract the repeated logic out and create a new method called check and spawn chunk. This method will take in a string called direction. The functionality of the method is just, well, its name, check and spawn chunk. It will check if a chunk exists in the specified direction, and if not, it will spawn a new chunk. Now let's simplify the chunk checker method by removing the lengthy if statements. Instead, we'll call the newly created check and spawn chunk method and pass in the direction name as an argument. In addition to this, we'll also modify the chunk checker method to include the additional checks for adjacent directions in the case of diagonal chunks. This adjustment ensures that the correct adjacent chunks are spawned alongside the primary diagonal chunk. So if you find this a little confusing, allow me to clarify. Let's consider the example of the primary direction being right up. So in this case, both direction contains up and direction contains right would evaluate to be true. For each of these cases, the check and spawn chunk method is called with the respective direction as an argument. What this does is that it checks if there is already a chunk in the specified direction, and if not, spawns a new chunk. Thus, to summarize, when the player is moving in the right up direction, the chunk checker method ensures that the chunks are spawned in both the right and up directions. This ensures that all possible paths that the player might take are covered within the new chunks. Essentially, the optimization just simplifies the code for the original diagonal checks while achieving the same outcome. Now, let's return to the Unity editor and conduct some testing. Everything should be functioning as expected, but now we have a more optimized and improved map generation. Excellent. Let's move on to other less notable errors that some of you have been facing. So the first thing to tackle is the missing details of the results screen, specifically when the player reaches the time limit and completes the run. So if you survive until the timer reaches its limit, you notice that only the time survived is shown, while the other details are missing. The reason for this is relatively straightforward. If we examine the game manager script, specifically the update stopwatch method, we can see that we simply call the game over method once the stopwatch time reaches the time limit. However, in the player stat script, all the assignment of the details for the results is done in the kill method. This actually poses a problem for us because by not calling the kill method, we're overlooking the inclusion of all the rest of these details. To rectify this, we can simply utilize the send message method as we did previously to call the kill method through the player object. By implementing this change, we not only address the missing details on the result screen, but also ensure consistency by calling the kill method instead of directly invoking the game over method when the player runs out of health. Now, when the player survives until the end, the result screen should show the details as per normal. So the second issue on the list of other code improvements is the issue of the player being able to collect pickups multiple times. So although this issue might not be as noticeable as the previous one, it's worth discussing as some of you have pointed it out. To test this issue, add a blue gem to your game scene and set the pull speed on the collector object under the player to be 0. This means that the item will not be pulled to the player. Afterwards, when in game, simply move in and out of the vicinity of the blue gem. You'll observe that the player is able to gain experience from the blue gem multiple times. This happens because the player collector script doesn't have a check to prevent multiple pickup collections from happening. Fortunately, there's a simple solution to address this problem. First, let's open up the pickup script. In this script, we'll just make a few adjustments. First, let's add a protected bool called has been collected, which will be accessed by the child classes, which is the pickups. This bool will be used to determine if a pickup has already been collected. Next, we'll just implement the iCollectible interface. To do this, add the iCollectible beside mono behavior in the script. Then, set the collect method to be public and virtual, allowing it to be overridden by child classes. Inside this method, simply set has been collected to true. Now, let's head over to the health potion and experience gem scripts. These are what we need to do. Now, since we already implemented the iCollectible interface in the parent class, which is the pickup class, we no longer need to implement it in the health potion and experience gem scripts, so we can simply remove the interface implementation from these scripts. Next, we need to override the collect method in both the health potion and experience gem scripts. Inside the overridden method, check if the has been collected bool is true. If it is, simply return from the method without executing any further code. If it is not true, call base.collect, which will execute the base implementation of the collect method from the pickup class. This base implementation will set the has been collected bool to true. Once the changes are applied, test the game again with the same setup. You should observe that regardless of the number of times the player comes into contact with the blue gem, they will only receive its effect once. After testing, do remember to remove the blue gem from your game scene and reset the pull speed of the player's collector to its initial value. Awesome! Before we move on, it's about time we make a change that has been long overdue, which is transitioning from using the Text UI to TextMeshPro. If you're not already familiar with TextMeshPro, let me introduce you to this game-changing tool. So in essence, TextMeshPro is just a better and upgraded version of the Text UI component. And from this point forward, we'll be utilizing TextMeshPro for all text-related elements in our game. Why, you might ask? Well, let me introduce you to some of the advantages TextMeshPro has and why it far surpasses the legacy Text UI in multiple aspects. So first and foremost, TextMeshPro offers superior rendering quality and performance compared to its predecessor. Now, you may have noticed that when reducing the font size in the regular Text UI, the text tends to appear blurry. However, with TextMeshPro, this is no longer an issue. TextMeshPro is able to provide crisp, high-definition text regardless of resolution or scale, which is very useful for games that caters to various devices and screen sizes. TextMeshPro also offers a wide range of additional features that enhances text appearance and functionality. With it, you will have greater control over text styling, including advanced typographic capabilities such as kerning, tracking, and vertical alignment. You can also add in text to apply custom formatting, color changes, and even hyperlink support to your text. These features provide flexibility and creative freedom when it comes to designing visually appealing text elements for your game. And this is just the tip of the iceberg. If you'd like to find out more about the key differences between Text and TextMeshPro, I recommend you check out Unity's official guide. So how do we add TextMeshPro into our project? Well, if you have been following along since the start of this tutorial series, chances are you already have the TextMeshPro package installed in your project through the 2D project template we selected at the start. However, if you're unsure or not whether you have it, here's what you can do. First, open the Unity Package Manager by selecting Window from the main menu and then choosing Package Manager. In the Package Manager, click on Packages and select Project. And if you have the TextMeshPro package, it should show up. And if you don't have the package, you simply need to install it. So to install it, you just click on Packages again and head over to Unity Registry and search for TextMeshPro. Afterwards, click on the TextMeshPro package to select it and then click the Install button at the bottom right hand corner of the window. Let's start by importing the essentials. Right click on the hierarchy and navigate to UI, Text, TextMeshPro. As this is the first time you're adding a TextMeshPro object, the editor will actually prompt us to import the essentials. Simply click on Import TMP Essentials and allow the importer to handle the necessary steps. Once you have completed the import process, close the importer window. Great! We now have TextMeshPro implemented into our project. Feel free to delete the TextMeshPro UI object that we just created as it is no longer needed. Next up, as you might have already guessed, we have to proceed with the task of replacing all instances of text with TextMeshPro. Now this can be a very time-consuming process if done manually, but fortunately there's a handy asset available on the Unity Asset Store that can actually automate this process. So the asset I'm referring to is called the TextMeshPro Upgrade Tool made by Circular. You can find the link to this in the description box below. Now don't worry, this asset is completely free and automates the process of replacing all text objects with TextMeshPro objects and updating the corresponding code references. This is a very handy tool and I highly recommend it. Before proceeding, I also highly recommend you to save a backup of your project. So the package should work for our current Unity version, which is a higher version than 2019.4.26, which the package supports, but it is always good practice to back up your project before implementing any external packages, especially from the Asset Store. To begin, let's head over to the Unity Asset Store and add in the TextMeshPro Upgrade Tool to your account. Now once you have added it into your Unity account, head back into the editor. Head on over to Window, Package Manager and make sure Packages is set to My Assets. Next, navigate to the Text to TextMeshPro Upgrade Tool asset and click on the Download button in the bottom right hand corner. Once you have finished downloading, you should see an Import button. Simply click it. Afterwards, a window should pop up asking which parts of the package you would like to import. Ensure everything is checked before clicking Import. Let the importer do its thing and wait until the package is installed. Now once the TextMeshPro Upgrade Tool is installed, you'll notice an addition of a new plugin folder into your project. Make sure not to touch it. Now let's proceed with the upgrade process. Select the Upgrade Text to TMP option from the drop-down menu under the Window tab. This action will open a new window specifically for the Upgrade Tool. Within this Upgrade Tool window, you will find a list where you can add in the different assets you wish to upgrade. Let's add in the game and menu scenes. Feel free to also include any additional scenes that are relevant to your project. For now, it is recommended to leave the settings related to the TMP font as their default options. Now once you've added in the scenes you want to upgrade and have confirmed the appropriate settings, you want to proceed by clicking on the large Start button located at the bottom of the Upgrade Tool window. Now at this point, a warning pop-up should appear, which you should acknowledge. Moving on to step 1 of the upgrade process, you'll be prompted to upgrade your script references to TextMeshPro. Now to ensure that all scripts are included in the upgrade, it is recommended to check the Toggle All option at the top of the window. Afterwards, you can simply scroll down and click on the Upgrade Scripts button. Once again, be sure to acknowledge any warning pop-ups that appear during this process. After completing step 1, you'll be guided to the next step, which is step 2, which involves upgrading components to TextMeshPro. Now once again, it is advised to check the Toggle All option to ensure that all components are selected for the upgrade. Finally, you'll reach the last step, which involves reconnecting the references. Now this step is straightforward. We just need to click on the Reconnect References button, which will save you the hassle of manually assigning the inspected references. Now once the upgrade process is complete, you can close the Upgrade Tool window and then proceed to refresh your scenes individually. Additionally, if you check the console window, you should be able to see the logs indicating that your project has been successfully upgraded. If you select any of the text elements in the game, you'll notice that they now have the TextMeshPro UI component instead of the previous text component. Similarly, if you select any of the components that previously had a text field, you will now find that it has been replaced with a TextMeshPro UGUI field. This is thanks to the last step, which is the reference reconnection. Now go ahead and make sure everything is working by starting the game and playing. Brilliant! We have upgraded all our assets and scripts to TextMeshPro flawlessly. Before we move on, let's address one final improvement to make our code even cleaner and more maintainable. Now if you open the game manager script, you'll notice that all the previous text declarations have been changed to tmpro.tmp_text, which is fantastic. However, you might notice that each declaration explicitly specifies the namespace tmpro. While this is not technically incorrect and our code will still function properly, we can actually make it cleaner by using a statement to import the namespace at the top of our file. To achieve this, let's add a using statement for the tmpro library and remove all explicit namespaces specifications throughout the script. But before we proceed, some of you who are familiar with TextMeshPro might be wondering about the difference between TMP text and TextMeshPro UGUI. Now normally, when working with TextMeshPro, you would use TextMeshPro UGUI for the Unity system. Usually, we work with TextMeshPro UGUI or TextMeshPro, which are subclasses of TMP text. However, it is not wrong to use TMP text because they are derived from TMP text. Thus, we can treat them as TMP text when using common features. Nevertheless, you are free to use either TextMeshPro UGUI or TMP text based on your preference, as it won't affect our game in any significant way. Let's also do the same for the other scripts, mainly the inventory manager and player stat scripts. Moving on, let's add a visual cue to our items. Visual cues play a vital role in enhancing the gaming experience, guiding players to important elements such as collectibles or power-ups. One commonly used visual cue is the bobbing animation, where an in-game object smoothly moves up and down. This animation creates a sense of motion and attracts the player's attention, and we will be adding such a visual cue to our game to boost flair and intuitiveness. Now, there are different approaches to implementing this animation, such as using an animator controller or coding it directly. In this case, we'll opt for a code-based approach to provide more flexibility and customization options. Let's begin by creating a new script called bobbing animation under the pickups folder. Inside of the script, we'll start by defining 4 variables. First variable will be frequency, which controls the speed of the bobbing effect, determining how quickly the object moves up and down. The second will be magnitude, which controls the range or height of the bobbing effect, determining the distance of the object moving up and down from its original position. Third will be direction, which determines the axis along which the bobbing effect occurs. And last but not least is initial position, which will store the original position of the game object before applying the bobbing effect. We'll use this to calculate the object's new position during the animation. Let's store the original position of the game object in the initial position variable in the start method. And in the update method, let's update the position of the game object every frame to create the bobbing effect. I know this looks like a lot of math, so here's a breakdown. So this part generates a wave-like value that oscillates between -1 and 1 over time. The mathf.sine function creates this wave, and multiplying it by time.time multiplied by frequency adjusts the speed of the wave. This part applies the wave value to the specified direction and takes in the direction vector, example up, down, left, right, or any combination, and moves it back and forth based on the wave value, which creates the movement in the desired direction. Now, this part adjusts the magnitude or range of the movement. By multiplying the direction with the wave value and then by the magnitude value, we control how far the object moves in each direction. Increasing the magnitude value amplifies the movement, while decreasing it reduces the range. Lastly, this part combines the original position of the game object, which is initial position, with the calculated movement. Now, adding this movement to the initial position ensures that the game object moves from its original position rather than from the origin. In simpler terms, all this does is that it creates a bobbing effect by repeatedly moving the game object in a specified direction from its original position, with the movement changing in a wave-like pattern over that time. Now, return to the Unity editor and navigate to Prefabs Pickups. Add the bobbing animation script to both the blue gem and red potion prefabs, and afterwards customize the field according to your preferences. For example, you can set the frequency to 3, magnitude to 0.1, and direction to 0, 1, 0 for a small up and down bobbing effect. Now playtest the game and you should see the pickups now have a animated bobbing effect. This visual cue adds a touch of liveliness and attracts the attention to the collectible items. Great! Alright, since we have covered the code improvements, it's now time to prepare the game for building. There are several steps we have to take before we are able to do so. First up is customizing the level design of the game. Now throughout this tutorial series, we have built various mechanics and features, and now you have the power and flexibility to create a level that aligns with your vision. To start, let's organize the hierarchy by moving the experience bar holder over the screens. This will ensure that it doesn't show above the screens in the game. Next, it's time to experiment and playtest your game to your liking. Modify the different values of the game such as the character and enemy stats, drop rates, and other variables. This is where you can really let your creativity shine. For example, you may want to create more challenging waves of enemies or adjust difficulty progression. Feel free to adjust any values to make the game more enjoyable and balanced to your liking. There's not much to say here because this step is just all about tailoring the game to your preferences and creating a unique experience. Take your time to iterate and fine-tune the gameplay until you're satisfied with the results. If you're in need of inspiration, you can just follow my settings. Enjoy the process of customizing your game and don't hesitate to experiment and test different configurations to find the perfect balance for your game. Now that we are satisfied with the level design of our game, the next step is to choose a suitable resolution. Now, do not overlook this, as selecting the right resolution of your project is very crucial as it affects the visual quality, clarity, and overall player experience. This resolution that you will choose will not only determine the sharpness of the graphics, but also impact the layout and sizing of the different UI elements. It's important to consider the target platform and the preferences of your intended audiences when selecting a resolution. In my case, I plan to build the game for WebGL to be played on browsers. Thus, I will choose a resolution that matches that well. To select a resolution, navigate to the Game tab. You will find a resolution drop-down at the top left corner. Click on it and choose the desired resolution. If the resolution you need is not listed, you can always create a custom resolution by clicking the plus sign at the bottom of the drop-down. The resolution I'll be selecting is 1280 by 720, which aligns with my goal of building for WebGL. Take your time and choose a resolution that best suits your game and target platform. Remember, the resolution you select will have significant impact on the overall visual quality and user experience of your game. Now once you've selected your desired resolution, you will likely notice that the UI elements in your game no longer appear correctly. They may appear too large or too small for the chosen resolution. To resolve this, we need to manually adjust the size of each UI element to ensure they are properly scaled for the chosen resolution. Although this process may be time consuming and a bit tedious, it is crucial to ensure that the UI elements look normal and are legible. Now, when resizing the UI elements, I really recommend you to modify the width and height properties of the elements themselves rather than simply increasing their local scale, because this approach will help prevent potential issues that may arise later on. Take your time and go through each UI element in your game by adjusting their sizes accordingly, paying attention to the font sizes of any of the text elements as well. By resizing the UI elements to fit the chosen resolution, we basically just ensure that the game's visuals are presented optimally. Great. Now, let's proceed with creating a basic title screen that will welcome the player when they first enter the game. To begin, let's create a new scene called title screen, which will serve as the container for our title screen, allowing us to have a separate scene before transitioning to the main menu. Now within the title screen scene, let's create a canvas object which will hold our UI elements. Afterwards, let's create a button to the canvas and name it Start. This button will be used to transition to the main menu. Afterwards, create a empty game object called SceneController and attach the SceneController script to it. Set up an on-click event for the Start button and assign the scene change method from the SceneController script to it. At this point, you may notice that our title screen may appear a bit empty. If you already have a background image prepared, you can add it to the scene as an image UI element. However, if you don't have anything like me, let's use some existing props from our game to create a visually appealing title screen. To achieve this, let's create an empty game object called title screen props to group our props. Afterwards, let's place a terrain chunk prefab in the scene as a visual element. Next, add some enemy and pickup objects to the scene. Ensure that you remove all scripts from the enemies and pickups except for the bobbing animation script applied to the pickups. I'll also be adding the title of our tutorial series to the title screen. If you like, you can download it from the description box below. You should now have something like this. Let's add the title screen scene into the build settings for the scene changes to work. Next, let's make some adjustments to the button functionality in the game scene. We want the quit button under the pause screen and the done button under the results screen to transition back to the title screen instead of the menu scene. After making these changes, test the transitions. Clicking quit or the done buttons should bring you back to the title screen. Before we move on, we can also add an instruction screen within the title screen scene to provide guidance on how to play our game. First, let's create a new panel in the title screen scene and name it instruction screen. Add a TextMeshPro UI element as a child of the instruction screen panel and name it instructions. Within this UI element, enter the instructions for the game. Let's allow players to toggle the display of the instructions. There's a simple way to do this without any code. Now, duplicate the start button and rename it to instructions button and position it as desired. Modify the appearance of the instructions button to differentiate it from the start button. Let's also add a on-click event to the instructions button and drag the instruction screen object into the event slot. Select the game object component of the instruction screen in the event slot and choose the set active method. Ensure that the checkbox is selected. Additionally, duplicate the instructions button and make it a child of the instruction screen. Rename it close instructions. And now in the on-click event for the close instructions button, untick the set active method to disable the instruction screen. With these steps, the instructions can be toggled. Awesome! Now it's finally time to build our game for the very first time. To start, go to File, Build Settings. Here, you'll need to select the platform in which you want to build for. In my case, as I've stated previously, I'll choose WebGL since I want the game to be playable in the browser. If you're building for PC, there's no need to switch platforms. Once you selected the platform, you need to open player settings by clicking on the player settings button. In here, you want to navigate to resolution and presentation. Here, make sure to manually enter the resolution you previously chose for your game. If you're building for PC, you may need to untick the default is native resolution checkbox to input the resolution values. After entering the resolution, close the player settings window and return to the build settings window. Now click on the build button and choose the folder where you want to save the build files. Finally, wait for the build process to complete. Once it's done, you successfully built your game for the first time. Now, run the build game and make sure it plays well. Take some time to playtest and verify that all the features and mechanics are working as intended. Congratulations, we finally built our game. That's all for this part. In this part, we touched up on certain aspects of our project such as identifying and fixing bugs along with some aesthetic changes. I hope you all enjoyed the video, and if you want to support what we do, you can actually help us by becoming a Patreon. This will give you access to the project files for tutorials, like this one, as well as any Patreon exclusive posts on our blog. You can find the link to this in the description below. Any support that you give us will actually go a long way, because currently we are making back about 20 cents for every single dollar that we put into content creation. So your help will actually go a long way to help us make this a sustainable endeavor. So that's all. I'll see you all in the next part. Bye!